A SNARK lets an untrusted prover prove, to anyone in the world that it knows like some data satisfying some, and we typically call that data a witness. Okay. Some specific examples of witnesses that come up in many applications, like in blockchains, like a natural witness that entities might be interested in proving they know is like a bunch of digital signatures authorizing a bunch of blockchain transactions. And the idea would be, without the SNARK, those digital signatures would have to be kind of stored and verified by every blockchain node in the world. So like on Ethereum today, there's maybe 600,000 entities that are sort of following along with the blockchain. And they are, verifying the signatures on every transaction and processing every transaction. So you might imagine, something like a roll-up is trying to keep as much, data and computation off-chain as possible. And so, rather than having every single blockchain node in the world, all 600,000 of them, like verifying digital signatures for every transaction, instead, we can have, a powerful but untrusted off-chain entity verify the digital signatures themselves and merely prove to the blockchain nodes that the digital signatures, were known and verified. Sort of a simpler example might just be proving that a secret key, that matches a public key. So in slightly other language, another way to say this is like, I could publish a password, not a password, like a hash of a password, a cryptographic hash of a password. And then, so that would be like my public key is like this hash of a password. And I could use a SNARK to prove that I know the password, like the secret key that hashes to that hash value I published. And in that way, so this is useful for like authentication. So I can basically, if I pick like a random password with lots and lots of entropy in it, like no one else in the world should know that password other than me, and no one should be able to guess it. And so by proving that I know the password, that sort of matches the public hash, I am thereby proving that I'm the same entity that published that hash in the first place. So that's what a SNARK is it lets you, it lets an untrusted prover prove they know some data satisfying some property, and that data is typically called a witness. Now, in some contexts, like where the data is a secret key, the witness itself is sensitive. It's like private information. And in those settings, you would want the SNARK to satisfy a property called zero knowledge. So a SNARK is zero knowledge or ZK if it reveals nothing, no information at all about the witness, besides that it satisfies the property that the prover is claiming it satisfies, so besides that the witness satisfies the claimed property. Right. So in particular, this sort of secret key, this, think of a secret key as like a password. If I want to prove to you that I know this password, like I could just give you the password. That would prove to you that I know the password. And, like if there's like a public hash of the password already known, like for once I tell you the password, you can check that the password is valid by just hashing it yourself and confirming that the hash of the password I gave you matches, the public hash. But that would be, like a gross violation of privacy. In particular, then the verifier knows your password and can, impersonate you forevermore. If this is like the secret key controlling a Bitcoin wallet or an Ethereum wallet or something, then, telling somebody the secret key lets them control your wallet and take all your assets or whatever. So in these applications where the witness itself is sensitive, you're really going to want this ZK property. But in other applications like this, this roll-up application I mentioned before, kind of keeping digital signatures and the verification like off-chain, the witness is not sensitive. And so here we don't really need ZK. What really matters here is that the SNARK is succinct. So the S in SNARK stands for succinct, and that basically means the following: that the proof is short and fast to verify.
Question, Justin. So what are ZK rollups used for them?
Yeah, so ZK in that context and as it's often colloquially used is really a misnomer. So in what people call ZK rollups, what we really don't care about, they have nothing to do with privacy. So really you only want the succinctness for ZK rollups. Some people advocate calling them like verifiable rollups or validity rollups or something like that to get rid of the misnomer. But we seem to be kind of stuck with the ZK rollups terminology. And to say just a little bit more about that, like succinctness is useful because like the verifier is like saving work, compared to the trivial proof system, right? So the trivial proof system, by what I mean by that is when the proof is just the witness, right? And the verifier just checks the witness itself for validity. And succinctness just requires that the SNARK verifier is like cheaper than the verifier of the trivial proof system. And cheaper means one or two things. So it means the proof is shorter than writing down the whole witness, and ideally the proof is faster to check than what's required to actually check the witness if somebody handed it to you. So the thickness is what's important for ZK rollups. Like the idea is you're thinking of the blockchain itself as a computationally very limited verifier. Because anything that the blockchain does, what that really means is every blockchain node in the entire network has to do all that work. It's like massively replicated work. So the dream is hard computations happen off chain, but anything that's off chain, like you can't trust. And those computations are proven. So like SNARK proofs that those computations were done correctly. And it's the proofs that are posted and verified on chain. And in this way, you're thinking of the blockchain as like a computation limited verifier, and the off-chain entities, whether it's a rollup or something else, quote ZK coprocessor or something, does the hard work and merely proves to the blockchain that the work was done correctly. Did that answer the question?
Yeah, that's great.
Great. Yeah. So ZK is really about privacy. So you'll see like actual ZK used in applications like private payments. So you see this in like Tornado Cash or Aztec or all sorts of other privacy focused projects in blockchains. Penumbra and stuff. But the ZK rollups today, at least, are not privacy focused, and they really just need the succinctness property. Okay. Other questions? And again, please don't be shy. If you have a question, someone else has the same one. Okay. So briefly, like what? So what does the SNARK term stand for? So S is for succinct, which again means that the proofs are short and fast to verify. N means non-interactive, and this means that the proofs, are like static strings, that you can just like post to the blockchain for any blockchain node in the network to verify. This is in contrast to like an interactive proof where the prover might send a message and the verifier then responds with some like random unpredictable challenge, and the prover responds to the challenge and the verifier sends another challenge and so forth. And so the interactive proofs are less of a good fit for like applications like blockchains, because the proof can't just be like posted to a website or broadcasted to all blockchain nodes to just be stored and checked at their leisure. The proof actually involves some kind of back and forth between who's ever verifying the proof and the prover. And then the ARK stands for argument of knowledge. And obviously in this study group, we'll learn in detail like what that means. But basically that just means security. So what it means is like provers cannot find convincing proofs of false statements. At least not without breaking some crypto system or something. So what that means basically is if somebody produces a proof that they know some witness, they must really know the witness. Because if they didn't know the witness, the only way they would have found that proof is by like, finding a collision in a collision-resistant hash function or something like that. Something that we think is totally impossible for, computers to do. Unless they spend like trillions of years of compute power or something like that. So that's a SNARK. Again, proofs are short and fast to verify. They're non-interactive, so they can just be posted to a blockchain or posted to a website or something, and they're secure. If you see a SNARK proof that verifies, the claim that the prover was making must be true. So that's what a SNARK is. And then so for today, my main goal is to present a high-level overview of the landscape of SNARK design. And then starting next week, we'll kind of start at the beginning of the book, like the technical details of how you actually build a SNARK. But I think before we start from square one of the technical details, it's actually helpful to have in your head kind of where it's all going, right? So I sort of start at the end and then jump to the beginning. All right. So this is how people think about SNARK design at a high level. By the way, if everybody else, I'm getting some feedback. Again, there's enough people now that this used to not be an issue, but now anyway, if you just double check, you're muted. Okay, so the idea is this is still a little bit aspirational, but this is certainly where I think things are going in terms of how SNARKs will be deployed in the long run. So the idea is like a developer, like a programmer, will write a witness checking procedure. Okay, so this is like a computer program that takes as input the witness that the prover claims to know, okay, and checks that the witness is valid. So again, in the example of verifying a bunch of digital signatures, so the blockchain nodes themselves don't have to do the verification. Like this computer program would take as input the signatures and their associated transactions that were and verify every signature actually verified. And verifies the witness, right? So that's what like the SNARK toolchain will kind of ingest from the developer. The developer who wants to deploy a new SNARK might know nothing at all about how SNARKs work. but they do know how to write computer programs. And so they're going to write a computer program that specifies, the witness checking procedure, right? And now what the tool chain will do is it will feed that program through what's called a front end. Okay, and the front end will spit out something. it'll transform the computer program basically into a lower level representation, which I'll talk about in a second. And that lower level representation is typically called an intermediate representation, or an IR. And I'll say more about these intermediate representations in a second. Okay, and then that IR is fed into what's called a SNARK backend. Okay. All right, so let me say more about what is an IR. So these intermediate representations, they tend to be basically circuits or generalizations thereof. And like the generalizations people normally consider are something called constraint systems. Okay, so if you've spent a little bit of time around SNARKs before, you'll know what I'm talking about. These are things like R1CS or algebraic intermediate representation or Planckish constraint systems. But the details right now aren't important. What is important is that like the proof machinery underlying SNARKs, the backends, they don't apply directly to high level computer programs like what a developer might write in Rust or something. Right, so you can't just like take a SNARK backend and like apply it directly to a Rust program. So the same way like your laptop doesn't like directly execute Rust code. Instead, the Rust code gets compiled down to machine code, and then your laptop directly executes machine code. This front end is meant to go from like the high-level computer programs, like a Rust program, down to like the SNARK equivalent of machine code. And so this intermediate representation is something like analogous to machine code for your laptop. So it's like the machine code of SNARKs. Okay, and then the SNARK backend is sort of like the SNARK analog of your actual hardware, like your laptop, and so it actually like applies directly to the machine code. That is the IR, the circuit or constraint system. And as we'll see throughout this reading group, the analogies between SNARK design and like actual hardware design and how computers work today go shockingly deep. So they're like not the same things, right? Like your actual laptop, which is a physical machine, is like not the same as a SNARK backend. But the analogies between how it seems to make sense to design computers today and how it makes sense to design SNARKs seem to go much deeper than you would think on day one of studying SNARKs. So yeah, anyway, so this is it's like a two-stage tool chain. Again, the developer is going to write a witness checking procedure. That's just like a computer program that takes as input the witness and confirms that the witness satisfies the property the prover is claiming it satisfies. The front end is going to turn that computer program into an intermediate representation, and then we apply a SNARK backend for that intermediate representation. And you sort of put the front end and back end together, and that lets the prover basically prove that it correctly ran the computer program on a witness. Okay, any questions about front ends and back ends? Okay, so yeah.
Justin, can you clarify in what sense this is aspirational? Because these technologies seem to exist already.
Yeah, great. So it's increasingly less aspirational. So this is, as I've described it, this is sort of the vision of ZKVMs, which are literally like basically implementing, this vision where the developer will write in a standard high-level language like Rust, and it'll go through this front-end back-end paradigm. Before the popularity of ZKVMs really, kind of took off. So if you go back, even 6 months or something, typically the developers were not writing in high-level languages like Rust. They were writing in much lower-level languages. And actually, this was maybe I'll spend a few seconds on the landscape here sorry, I had some notes on this. Well, let me just pull it up. Here we go. So I guess I could call this example front ends real fast. Answer this question just with some examples. So so front ends, and these also sort of get it's hard to distinguish between a front end itself and what's called a ZKDSL. This is a domain-specific language. So let me just give some examples. So like Bellman and CIRCOM are very popular, and these are basically they have the developer specify the witness checking procedure, like not in a very high-level language like Rust, but in quite a low-level language. Basically, the developer is directly specifying the circuit or constraint system. So the witness checking procedure is specified in a low-level hardware language. This is almost like the developer like writing down the constraint system constraint by constraint, or writing down the circuit gate by gate. And then there are other projects that sort of expose to the developer a slightly higher level language. So there's like Socrates, XJSNARK. I guess like Cairo assembly was sort of originally characterized as slightly higher level than constraints or circuits. And so these are what I would call ZKDSLs that are a little bit higher level languages than Bellman and CIRCOM, but still very low level. And it's like a continuum, I'd say, like a step up in terms of how low level the language is. Might include things like Noir. I think would be considered higher level than something like Socrates or XJSNARK. And then eventually you just get to Rust, or pick your favorite high level language that people use all the time today. Let's just use Rust as our example. This would be the highest level thing. So today the idea is, a very popular approach, which I think, people might be converging around, although it's still not, totally clear, is that like the Rust would get compiled down to the machine code, literal machine code, for a simple CPU architecture, like RISC-V. And the back end, this machine code would be fed into a back end for the CPU. Examples here being like RISC-Zero's back end, SP1, or Jolt. And so I'm used to giving this. The last time through this reading group was started a year ago, and it was before the like ZKVMs for RISC-V were quite as popular or developed as they are now. And so I'm used to saying, this front end back end paradigm with the programmer writing a Rust program is aspirational. And what I was getting at was, like the prevailing approach involved people, writing in Bellman or CIRCOM, or like constraint systems in Halo 2. And there, it's like you almost don't have a front end, right? It's like the developer itself is like writing down the circuit. And so the notion that the developer like doesn't have to know anything about intermediate representations and can just write, the program the same way they would, if they weren't using a SNARK at all, hadn't really taken hold yet. Hopefully that answered the question. And any other questions? All right. Okay, so that's a little bit about front ends and like how the tooling is, probably going to work. And there is a lot up in the air still, I'd say. I think, look, one of the main reasons people are trying to move away from these very low-level ZK DSLs is, it takes a lot of human effort to design, to express these constraint systems, these circuits. The human has to have quite a bit of domain knowledge, to get used to writing these constraint systems. It's just time intensive and unpleasant. It really just doesn't scale in a human effort, view of things. And also, like, these constraint systems are basically always buggy. And you can, there's been a bunch of work to bring formal verification methods to bear on the constraint systems to try to, detect the bugs and confirm that there are no bugs in the constraint systems, that the constraints actually capture the high-level witness checking procedure that the developer intended. But like, that just is, makes the human, effort and lack of scaling even worse. So it's like, you either apply the formal verification techniques and maybe you do get some kind of formal guarantee that the constraint system is bug-free, but you've just made sort of the scalability issue of human effort even worse, right? Since you now, in addition to expressing the constraint system, you have to go through the trouble of formally verifying it, and the tooling for that is still fairly primitive and stuff like that. So, the idea of these ZKVMs especially for existing instruction sets like RISC-V is, the developers can just write their Rust programs the way they would, even if there was no SNARK. They don't have to learn a new ZK DSL. It's much higher level and just easier to write than specifying the constraint systems by hand. And on top of that, we can kind of piggyback on existing tooling, right? Because there's a massive industry effort to develop good support for Rust and compilers from Rust down to like pre-existing C instruction sets like RISC-V. And if we're designing like our own CPUs Thaler to SNARKs or things like that, we can't piggyback on the tooling as much. So you both have to, sort of put in the man hours to the human hours to redesign the tooling. And also, as soon as you do that, like, you now have new tooling that hasn't been scrutinized as much as the existing tooling, hasn't been subjected to, the formal methods for confirming there's no bugs and stuff. And you can try to do that all over again, but it just really doesn't scale. So that's sort of, I think, the current ethos, and but there are trade-offs all over the place. Generally speaking, you can definitely still gain better SNARK performance, like basically faster prover or something like that, if you eschew the ZKVM approach. But then you're, it's worse for the developer who has to write circuits, and the circuits are likely to be buggy, and so your SNARK is not secure in the end, things like that. And we'll be discussing all of these issues like ad nauseum throughout this study group. Okay, so that's back end. I mean, that's front ends and just like kind of SNARK tool chains. Let's talk about back ends, right? So backends, again, they are the actual SNARKs, right? So typically these backends apply to some kind of circuit or constraint system. Again, there is fragmentation in the space. in terms of what kind of constraint systems people like to use. And you know, if we coalesce around the ZKVM approach, like that, that fragmentation will start to go away a little bit. But let's ignore, you know, those issues right now, and just talk about generally how SNARK backends are designed. So SNARK backends typically have two components. Really, they're designed in a three-step process. So three-step design process. And this discussion is going to be a little bit technical, but you know, we have months to fill in the details. So don't worry if I'm about to throw out terms you've never seen before. So when designing a SNARK backend, the first thing you'll do is design something called a polynomial IOP. That is, you know, a technical sounding term. I'll tell you in a little bit, like roughly what that is. Don't worry about it at the moment. And then you design a cryptographic primitive called a polynomial commitment scheme. Okay, and you put these things together and you get a succinct interactive argument. Okay, but a SNARK, you know, the N in SNARK means non-interactive. So we're not happy with interactive arguments. So to get the N in SNARK, the third step would be to apply something called the Fiat-Shamir transformation. And that will just get rid of the interaction for you. And so it kind of replaces like random unpredictable challenges sent by the verifier in the interactive case with cryptographic hashing. And that way you get rid of the interaction and kind of replace it with cryptography. So this is how SNARKs are designed. And there are some mild exceptions. So the main, I'll say the main exception, maybe even just the only exception, is growth 16 and its predecessors. And so today, this is still actually the most widely deployed SNARK based on the data I've seen, even though the SNARK itself is from 8 years ago now. And, you know, and people really like it because it has very good verifier costs. Maybe it's not quite the best verifier costs. It depends on how you measure them. In terms of gas, I think maybe F-Flonk is a little better, but anyway, people like it. It has very good verifier costs. There are some reasons they also don't like it, but it remains the most popular today. And growth 16 almost fits into this design paradigm, not quite. So rather than using a polynomial IOP, it uses something called a linear PCP. Which is almost a polynomial IOP, but not quite. And it uses cryptography that's very similar to something called KZG polynomial commitments. Okay, and it actually doesn't need Fiat-Shamir. So the reason is it sort of pushes the need for Fiat-Shamir, like it gets rid of it by doing more work in what's called the trusted setup. If you don't know what a trusted setup is, don't worry about it. So my main point here is growth 16 does not quite fit into this paradigm, but it's barely outside the paradigm to the point where I basically don't even consider it an exception. So, you know, people might qualitatively disagree with me here, but I think even growth 16 is basically just about fitting into this paradigm as well, and there's really just no Fiat-Shamir needed. Okay, and so yeah, let me tell you now what is a little bit tell you a little bit about what is a polynomial IOP. Again, the details here, like we're going to cover like ad nauseum in a few weeks. So if you don't follow what I'm about to say, don't worry about it. But a polynomial IOP is basically so people abbreviate PIOP, and this is an interactive protocol where one or more of the prover's messages, so the prover P, may send to the verifier, which I'll denote with a capital V, large polynomials. Okay, and what by large polynomials, I really mean something like q of x equals, like 1 plus, x plus 3x squared plus 4x cubed, plus, something times, x to the n. Okay, and by large, what I mean is like n can be here pretty big. So think of n, in the millions or even the billions, millions, billions, even trillions maybe. Okay, so like the number of coefficients in this polynomial can be really big. In general, like if the prover is proving and knows a satisfying assignment to some circuit, like n is, certainly might be at least as big as the circuit size. So circuit size or bigger. So the point is like we don't actually want the prover to send all of the coefficients of this polynomial to the verifier. Because that would totally destroy succinctness, right? It's like writing down this polynomial is like worse than just writing down the witness that the prover is claiming to know, right? So in the polynomial IOP, we nonetheless let the prover send this big polynomial to the verifier anyway, right? We certainly don't want the verifier to have to read the whole description, right? So in the polynomial IOP, we give the verifier like very limited access to this polynomial. So that we give it what's called query access to Q. So that is V is allowed to evaluate Q, at say like 1 point, maybe 2 or 3 or 4, but let's just say 1 point, like Q of R for an R that the verifier chooses at random. Okay, and so for that reason, while we think of in the polynomial IOP, we think of the prover like sending the whole polynomial to the verifier. The verifier doesn't really need to know like all of the coefficients of this polynomial. It's only going to ultimately need to know like one evaluation of the polynomial. Okay, and so that's what a polynomial IOP is. It might seem, if you've never seen how SNARKs work at all before, which I assume is the case for many of you, this will look a little funny. Like, why should a proof, like contain a giant polynomial in it? And we'll see, like intuitively, the reason is polynomials have really nice distance amplification properties. And so what that means is if two polynomials are not absurdly high degree. So like, even though I said Q has large degree, like its degree is still like, it's like too big for the verifier, but still small enough for security purposes. So two polynomials of degree n that are not the same polynomial, it turns out that they disagree at almost all inputs. And so that's like a very nice kind of distance amplification property where like if the prover sends a polynomial Q prime, which does not equal the polynomial Q it's supposed to send, somehow like the verifier is able to pick up on that kind of cheating action by the prover really easily because when it, if it evaluates Q prime at a random point R, then with overwhelming probability, Q of R and Q prime of R will not agree. So if, again, if Q and Q prime are two different polynomials and the verifier evaluates them both at 1 point, they'll spit out a different evaluation. So that's some intuition for why our SNARK proofs will often involve these polynomials. Polynomials are like a way to take two different objects that might differ in only like one coefficient and turn them into objects that differ, almost everywhere at almost all inputs. Okay, so that's what a polynomial IOP is. It's like this funny protocol where the prover is allowed to send these pretty big polynomials to the verifier, but then the verifier like only winds up evaluating the polynomial at a single point. And a polynomial commitment scheme is just exactly what you want. It's exactly what you need to avoid having the SNARK prover like literally send all of the coefficients of Q to the verifier. So polynomial commitment scheme is what you need to like turn a PIOP into a succinct argument. Okay, so basically, like rather than having the prover send, all of the coefficients of this polynomial Q to the verifier, instead, the polynomial commitment scheme lets the prover cryptographically commit to Q, right? And then, so it's like the commitment to Q will often be just like a single hash value or a single element of a cryptographic group. So it might only be like 256 bits or something. So Q itself might contain, gigabytes or terabytes of data or something, but the commitment to Q will only be like a few hundred bits. Once the prover commits to Q, it's almost as if the prover sent Q to the verifier, even though it didn't. Okay, and then what a polynomial commitment scheme is required to do is let the verifier later say, hey, you didn't literally send me Q, you sent me a commitment to Q, so I don't know Q, right? But despite that, I now demand that you tell me the evaluation of Q at a random input. And the polynomial commitment scheme lets the prover provide that evaluation along with the proof that the provided evaluation is indeed like the committed polynomial evaluated at the requested point. And so a polynomial commitment scheme, I'll sort of leave it as just vague as just one sentence. It's sort of exactly what you need to take a polynomial IOP, which is not succinct because, the prover like in the polynomial IOP like does send the whole polynomial Q, and make it succinct by sort of getting rid of the need for the prover to send all of Q. And it uses cryptography to do that. It uses, these so-called like binding commitment schemes to do it. Okay, so that is how SNARKs are designed. And what I'm going to do is give you a few examples of polynomial commitment schemes and polynomial IOPs. So I'll start with the PIOPs, and then I'll do example polynomial commitments. But let me just pause here and see if anybody wants to ask a question. Any questions?
I have a quick question, by the way. Since you touched upon it already, I don't know if it's the right time to ask this, but since you kind of pointed out that Groth16 is like linear PCP versus most of the things are PIOPs, and that linear PCP is quite close to PIOP, can you just tell the difference there?
Yeah, I'd say in a linear PCP, in the Groth16 linear PCP, like part of the proof is a polynomial or polynomials, but then like another part of the proof is another big message that is not quite a polynomial. And we're not going to cover Groth16 until like very late in this study group, so I won't be able to unpack that for a long time. But let's see. So yeah, but basically in a linear PCP, the prover, the linear means the prover's messages are linear functions. And linear functions are a little bit more general than polynomials. And so Groth16, by letting the prover sort of send messages, like long messages that are not just polynomials, it's able to get some nice properties that I guess the polynomial IOPs themselves, we don't know how to achieve from them. In particular, no fiat Shamir. But no fiat Shamir has some like interesting implications. Like it winds up making the Groth16 proofs like nice to aggregate in certain ways that polynomial IOP based SNARKs are not as nice to aggregate. But all of those benefits of Groth16 come at some kind of cost. In particular, there's what's called a circuit-specific trusted setup, and it's sort of the way it's getting rid of is like avoiding the use of fiat Shamir is by pushing a bunch of stuff into the trusted setup that none of the polynomial IOP-based SNARKs need. Yeah, so I guess I'll leave it at that. It's like if you have a linear PCP, you can still turn it into succinct arguments with the same kind of cryptography underlying some of the polynomial commitment schemes. So it's like it's okay that one of the prover's messages in the linear PCP is not literally a polynomial. Like the cryptography can still handle it and let the prover commit to it. It's just So there are both pros and cons that come from considering like some kind of generalization of polynomials to linear functions, and that's what Groth 16 is based on. Was that a little bit helpful?
Just one follow-up, Luke. So, what would be the right mental model? Is linear PCP more expressive than the PIOPs or less expressive, like in terms of?
I consider it a little bit more expressive because it lets the prover send like basically arbitrary linear functions. I don't want to go into detail right now about why linear functions can be viewed as like a generalization of low degree polynomials, but they can be. So in that sense, it's more general. The prover is not restricted to sending polynomials. It can send an arbitrary linear function, which is a generalization of polynomials. And nonetheless, we still have good commitment schemes that lets the prover commit to the linear function rather than literally non-succinctly send it to the verifier. On the other hand, so linear function is a generalization of polynomial. PCP doesn't allow interaction. So whereas the I in PIOP means interactive. So that's like so technically they're like linear PCPs are incomparable to polynomial IOPs. They're more general because they allow general linear functions. They're less general because they don't allow interaction. And the lack of interaction in the linear PCP though is like why Groth 16 is able to avoid fiat Shamir. Yeah, so technically linear PCPs are incomparable to polynomial IOPs. They're more general in some ways, less general in others. Is that enough color?
Yeah, sure. I mean, I was just a little. I questioned this when I read this because, in sense, even with PIOPs, the thing that we finally build is to a high degree like probabilistic at the end in form of proofs.
Mm-hmm.
And in the PCP also it's like probabilistically checkable. So I mean, just that the verbiage didn't make sense, but yeah, what you described makes sense. But I still have questions on why we chose those terms.
Yeah, and the terminology is tricky to dive into, I guess. I think that this will become clearer, in the coming weeks. We won't have to get all the way to Groth 16 for some of this stuff to make a little more sense. But yeah, the terminology is going to be a recurring, like struggle. I think, there's just a lot of closely related concepts. Everything ultimately in SNARKs kind of boils down to randomly evaluating, polynomials at one point. Regardless of what the underlying machinery is, it all boils down to like the fact that two different low degree polynomials differ at almost all their inputs. And because it's the same basic technique underlying everything, the differences between them, while important, can get a little confusing since the similarities sometimes outweigh the differences. So great question. It's just a tough one to answer in session one.
Just a quick question. What do we prove at the end of a polynomial IOP? Like, what is our goal here?
Yeah, I mean, I think the best I can do to answer that now is just say a little bit more about how these polynomial IOPs tend to work. Okay, so typically at least one of the polynomials that the prover sends in the polynomial IOP is basically like call it like an encoding of, like, it captures the witness the prover claims to know. Okay, so it's like the prover, the PIOP prover, like, takes the witness it claims to know, interprets it as a polynomial, and sends that polynomial. So it's like the coefficients of that polynomial are literally the witness the prover claims to know, right? And then the problem is the verifier is only allowed to evaluate this polynomial at one point. And so, somehow that one evaluation of the polynomial must encapsulate the entire witness. It's very strange. This polynomial, the witness itself might have 1 trillion entries in it. So the polynomial has 1 trillion coefficients, but somehow you can boil all of those trillion coefficients down to one evaluation of that polynomial. And that is enough information about the witness for the polynomial IOP verifier to ultimately ascertain whether the witness is valid or not. Okay, and then the other messages in the polynomial IOP that follow the prover, sending this polynomial encoding the witness, they are meant to as a reduction technique, right? So initially, the verifier sort of receives this polynomial encoding of the witness, but does it, wants to make sure that the witness is valid. Validity of the witness corresponds to many constraints all applied to the witness. And so the rest of the polynomial IOP, the other messages are there to sort of reduce, making sure the witness satisfies all of those constraints to just checking the value of one evaluation of that polynomial encoding the witness. Okay, so at the very end of the polynomial IOP, it's the prover is forced to make, it's maybe the prover sent a whole bunch of messages, received several random challenges from the verifier along the way. And, in the end, the prover is forced to make just one claim, this polynomial encoding of the witness evaluates to this value at this point, right? And that's the only thing the verifier checks in the end. Okay, is that enough color to make things a little more concrete?
Yeah, it helps.
Okay, yeah. So yeah, again, very hard. With the ZK property, there are a number of standard examples to convey the intuition. The where's Waddle example, where I can prove to you I know where Waddle is without revealing anything about his location by just showing you Waldo, but nothing about his surroundings. ZK you can give intuition for. The succinctness property, which these, polynomial IOPs combined with polynomial commitments is achieving, it's just like magic. It falls out of, the fact that, if the prover sent an invalid witness, once you turn it into a polynomial, that polynomial differs at almost all possible inputs from of any valid witness, turned into a polynomial. That's really where succinctness comes from. So you're somehow able to reduce, checking that the witness satisfies, all of the claim constraints down to one evaluation of the polynomial encoding the witness. That's where succinctness comes from. And it's really, I don't think anyone's found a better way to convey that besides, the sentence that just came out of my mouth, which is a very hard sentence to follow. So, that it'll all make a lot more sense as soon as 2 weeks from now, certainly by 4 weeks from now. But today, that's probably the best I can say.
Hello, I have a question.
Yep.
Where does zero knowledgeness fit into this diagram? Is it the IOP
yeah,
or the commitment?
that's a great question. So in a sentence, it doesn't. In my view, the right way to design a zero knowledge snark is to design a snark without worrying about zero knowledge, and then add zero knowledge in kind of later. And typically you can add zero knowledge in without a major hit to performance, either for the prover or the verifier. But it can be annoying and error prone and tedious. You see, the original Planck paper, just to highlight an example, had a bug in how they made it zero knowledge. And it was actually several years before anyone noticed there was a bug. And that's not a dig at Planck. It's just typically you can make these things zero knowledge with a standard bag of tricks, and the performance hit to the prover isn't major, but that doesn't mean it's super simple and straightforward. It's quite annoying to do. I can say 2 sentences about different ways you can add zero knowledge to a non-zero knowledge snark. Okay, so one is actually is very straightforward, at least conceptually, which is you can take your non-zero knowledge snark, so that proof does leak information about the witness the prover is proving it knows, and just don't declare that to be the final snark. Instead, use a zero knowledge snark like Plonk today, now that it actually, presumably has been correctly patched. Use the ZK-SNARK like Plonk to prove the non-ZK-SNARK proof. So that is a completely generic way to make the SNARK ZK. Just use a ZK-SNARK to prove the non-ZK proof. Okay. In some contexts, that's fine. Like this technique will not add much overhead for the prover or anything like that. In other contexts, maybe this would be a bottleneck, like proving the proof would be slower than computing the first proof, and so you're not happy, with the extra work you have to do to prove the proof. And so if in that situation, it is possible typically to sort of more directly make the SNARK ZK. And the way that tends to happen is the following. Like if the non-ZK SNARK had the prover send a bunch of like field elements or something to the verifier, those field elements might leak information about the witness. So we better not explicitly send those field elements to the verifier. Instead, what we'll do is we can do things like have the prover send a commitment to those field elements where the commitment is hiding. Okay, and if these words don't mean anything to you, it's not important, but hopefully you're just getting a little bit of the flavor. Like this all will make sense, in due course. It's like the prover, sends a hiding commitment to the field elements it would have sent in the non-ZK SNARK, and then later proves that like the values inside the commitments would have satisfied the non-ZK verifier. So it still has this flavor that like there's some non-ZK object, and then you're, rather than, like explicitly sending that non-ZK object to the verifier, you're using like a ZK object to like prove the non-ZK object. But hiding commitments are kind of lighter weight than ZK SNARK. So potentially, this approach is avoiding potential overheads of full-fledged SNARK composition, rather than using a SNARK that's ZK to prove the non-ZK SNARK. We're instead taking the individual elements of the non-ZK SNARK and like committing to them in a ZK way, and then later proving that the values inside the hiding commitments would have been accepted by the verifier. Hopefully that's enough flavor for now.
Great, thank you.
Great. Thanks for all the questions, and please keep them coming. I'll proceed now, but I think these questions are, I'll just forget to mention these important things if you don't ask about them. So keep them coming. Okay, so yeah, I think I can wrap up today's session in the next 15 minutes. So let me just give some example PIOPs and some example polynomial commitment schemes and discuss the trade-offs between them a little bit. And so I'll say before I give the examples, broadly speaking, you can take any PIOP and any polynomial commitment and put them together to get your succinct interactive arguments. So it's sort of like mix and match at will. There are some caveats to this, which is some PIOPs like to use univariate polynomials. Univariate polynomials are like this Q I wrote before, Q of x is like 1 plus x plus 3x squared plus 4x, there's one variable x. And actually most of the popular SNARKs today, PIOPs today use these univariate polynomials, but others, which are becoming more popular, use multivariate polynomials, and in particular, something called multilinear polynomials. Exactly what that means isn't important for now. And similarly, some polynomial commitment schemes, I'm just calling them PCs for now, polynomial commitments, apply specifically to univariate polynomials. Some apply specifically to multilinear, and some to both. And sort of you can, this is the main reason you can't mix and match at will. Like if your PIOP wants to use a multilinear polynomial, you can't combine it with a univariate polynomial commitment scheme, and sort of vice versa. There are some transformations known that will turn like univariate polynomial commitments into multilinear ones. Those transformations, however, can introduce certain overheads. So you might give up some of the really nice performance properties of the univariate one if you turn it into a multilinear one. And you can also view the same transformations in a sense as turning P, as the transformations, you could think of them as applying to the PIOPs rather than the polynomial commitment. So you could either think of the commitment scheme as getting transformed, from applying the univariate polynomials to multilinear ones, or you could think of the PIOP as getting transformed from using multilinear ones to using univariate ones. But anyway, so that's the main caveat. Different PIOPs and polynomial commitment schemes like apply or want to use different kinds of polynomials. Okay, so example PIOPs. So I break these into three categories. This is sort of, my personal preferred way of slicing and dicing the landscape of PIOPs. So, I don't know if other people think of things in the same taxonomy or not. So I'm going to list them sort of with the best verifier cost first, but the slowest prover first, and then gradually move to higher verifier costs but faster provers. So these tend to be in tension. Like the more work the verifier does, the less work the prover has to do, and vice versa. This tends to be the situation. So constant round PIOPs tend to have very nice verifier costs, and examples include Planck, Marlin, and the SNARK PIOP. The PIOP underlying SNARKs. And these all tend to use univariate polynomials. And again, growth 16 almost fits into a constant round PIOP. It's actually like a one message PIOP, if you will. And it's non-interactive. That's why it's just one message, but it's not quite a polynomial IOP. It's a little more general than that. It's a linear PCP. So let me just say almost growth 16. So yeah, these use univariate polynomials. They tend to be very good for the verifier, less good for the prover, as we'll discuss over time. Then you have, so the final two classes are related. One I call based on multi-prover interactive proofs, or MIPS. That's short for multi-prover interactive proofs. Canonical example here being something like Spartan. And then you had just interactive proofs. Canonical example here being something called the GKR protocol. Okay, and these are, both these classes use something called the sum-check protocol. Due to Lund, Fortnow, Karloff, and Nissan from the very early days of studying verifiable computing, so like 1990 or so. The sum-check protocol likes to use multilinear polynomials, not univariate ones. And generally speaking, these tend to have higher verifier, like bigger proofs, but they're still like logarithmic or polylogarithmic in size. I'll explain in more detail in coming weeks, like why sum-check based things tend to be faster for the prover than the stuff based on univariate polynomials. Okay, and then as far as polynomial commitment schemes go, I break these into three classes as well. So the first class I would classify, what do I want to call them? Let's say they're based on trusted setup. They have they use elliptic curve groups, specifically pairing friendly groups. But they so these are sort of, people might consider these bad things, I guess. But the good thing about this class of polynomial commitment schemes is they have really low verifier costs. So constant size evaluation proofs. When the verifier says, hey, tell me the committed polynomial evaluated at this point R, and the prover comes back with the evaluation and a proof that the evaluation is correct, these proofs are really small, like just like as little as one group element. And so the canonical example in this category is KZG commitments. Okay, and KZG commitments are specific to univariate polynomials. There are certain analogs of them for multilinear. like Zeromorph, Hyper KZG. There's a much older one called PST for the authors that introduced it. But these are for multilinear, but they have, unfortunately, logarithmic size evaluation proofs rather than constant. So that's why I was saying before that, like there are known transformations from certain multilinear polynomial commitments, univariate polynomial commitment schemes to multilinear ones, but they introduce overheads. This is an example where, one such overhead introduced is the proof size goes from constant number of group elements to logarithmic. Okay, so that's one class of polynomial commitments. The next I would say is related to the first class in that they use elliptic curve groups, not necessarily pairings, but they're transparent. So transparent commitments, but still using elliptic curves. So still curve based. Again, it doesn't necessarily need pairings. If you don't know what pairings are, don't worry about it at all. And so the most popular example in this category would be bulletproofs. And again, just as the most widely deployed PIOPs are in the sort of best for the verifier category, the most popular polynomial commitment schemes in each category that I'm covering are also tend to be best for the verifier. So in my view, there's just generally been a very heavy emphasis in SNARK design since the beginning on verifier costs. And so, the increasing popularity of sort of newer, different protocols is coming from, I think in part, more of a focus on prover time as a bottleneck, as opposed to verifier costs. So bulletproofs, people will also call this IPA for inner product argument, is basically because there was a paper that did most of the work in developing the bulletproof polynomial commitment scheme, and then the bulletproof paper optimized it concretely a little bit. So some people will call bulletproofs IPA to sort of try to be more precise about, I guess, where the credit belongs, I suppose. And so bulletproofs has quite small proofs. It's logarithmic size proofs, logarithmically many group elements. Okay, and it doesn't use pairings, so you can use any group in which discrete log is hard. It doesn't have to be a pairing-friendly group. The big downside of bulletproofs, it's a very slow verifier. It's actually, people call it linear time. It's actually super linear time. It's worse than linear time. And the prover is also slow, although, it's it's worse for the verifier to be slow than for the prover to be slow. So, yeah, anyway, so people consider this the big downside of bulletproofs. I think logarithmic size evaluation proofs is probably fine in a lot of contexts, but even though the proofs are short, they're quite slow to check. So there are some other examples in this category of transparent based on elliptic curves. One is Dory. So Dory no one really uses Dory in practice, but it's asymptotically, it's sort of like bulletproofs without the downside. So it's like bulletproofs with the fast verifier, which makes it sound pretty good, right? Bulletproofs with the log time verifier. But there are certain reasons people have not embraced Dory in practice. So, well, it does use pairings, that's fine. That's not a big deal. I'd say the main reason people haven't used Dory in practice is the proofs, while logarithmic size, they're 10x to 15x bigger than bulletproofs. I'd say that's one of the main reasons people haven't embraced Dory, even though they're asymptotically logarithmic. They're bigger, significantly bigger. There are some other technical reasons as well that aren't worth going into here. And then another one is Hyrax, which right now is not super popular. I'd say because the proofs are pretty big. They're square root size proofs, meaning if your polynomial that you're committing to has 1 million coefficients, the proofs will be still what's square root of 1 million, thousands of group elements. So that on the one hand, that's not great. On the other hand, the Hyrax proofs can actually be shorter, than some of the commitment schemes in the next category that are popular. So that doesn't mean that they're cheaper to run in terms of like gas costs or something, because they involve a lot of group operations. But it's at least something that I think more people should be aware of. Square root proof sounds big. Kind of concretely, it's not necessarily bigger than like polylogarithmic size proofs, which we're about to see in the next category. Okay, any questions about the first two categories? So you got KZG with trusted setup, and you got bulletproofs and others that do not have a trusted setup. Questions?
Is Dory the one with the groups of unknown order stuff in it?
No. So Dory does not use groups of unknown order. You could call groups of unknown order a fourth category. Is like a fourth category. I'd say they seem to just be impractical, unfortunately. At least, so the main example that was something called Dark, a work called Dark. The motivation was similar to Dory, where you're looking at bulletproofs, don't like the slow verifier, let's get a fast verifier kind of thing. Unfortunately, the main groups of unknown order that people thought might turn out to be practical were called class groups, and they were sort of they weren't really practical even then. And better attacks were discovered shortly after Dark came out, which made them like even more impractical. So I'd say as of today, you can. If your main focus is on practical snarks, you can kind of ignore the class groups category. But yeah, similar motivation to Dory anyway. So yeah, but I think Dory like actually could be practical in the near future. I haven't seen a path to groups of unknown order based commitment schemes being practical in the near future. They seem much further away from that. Other questions?
I was wondering, when you talked about the constant round polynomial IOP, is it constant in the sense that it's not dependent on the size of the circuit or the degree of the polynomial, or what?
Yes, exactly. So these tend to be like about 2 rounds. So like Planck and Marlin, I think, are like 2 rounds, or they might be as little as 3 messages, which is like the prover sends a message, the verifier sends a random challenge, and the prover sends one more message. And Groth 16 is actually just like 1 message. It's like non-interactive itself. So that's what I mean by constant round, is like 2. Regardless of how big the circuit is that's being proven, the number of rounds is 2. Whereas like the sum check based stuff, like they always involve at least about logarithmically many rounds, which in practice is like never bigger than log circuit size is never bigger than like 40 or something, but 40 is much bigger than 2, and like the GKR protocol actually involves log squared many rounds, and that can go up into like 1,000 or so. Yeah, so constant round means 2, and any sum check based things are kind of like 20 rounds and up, roughly. Yeah, so one of the really nice things about combining a constant round polynomial IOP with KZG commitments is when you have like 2 rounds and the commitment size is constant, like 1 group element, and the evaluation proofs, for the commitment scheme are also constant size, like 1 group element, then your end-to-end snark proof is just a constant number of group elements, right? And so if you want like the snark proof size to be a constant number of group elements, like the only way to get that is to take constant round PIOP and combine it with KZG commitments. And that's basically what Planck and Marlin and almost Groth 16 all do. And that's why these became so popular. But what's really going on though is there's this tension between prover costs and verifier costs. where, while, it's amazing you can get like constant size proofs, the prover winds up doing a lot more work due to the use of a constant round polynomial IOP. And that's why the sum check protocol is starting to gain more popularity to get the prover a little faster. But then you can't hope for the proof size to be lower than logarithmic unless you bring in SNARK composition, which I'll discuss. I mentioned in response to a question before about ZK, and I'll discuss briefly again in a few minutes. Other questions?
Intuitively, I would have assumed that there should be a relationship between the verification time and the proof size. But then for bulletproofs, you had stated that the proof size is logarithmic. However, the verification is super polynomial or super linear or something. I don't understand how that works exactly.
Yeah, it's a little tough to explain. I think with the exception of bulletproofs, I think you're right. Like shorter proofs tend to lead to faster verification. But there are some caveats, and one is how do I want to say this? Like with bulletproofs, there is what's called the public parameters or the commitment key or something. It's as big as the polynomial being committed. So this is like a big string that anybody who wants to commit to polynomials with bulletproofs needs to know. And in bulletproofs, the verifier also has to know that string. Okay, and even reading that string is linear time. And the bulletproof verifier, it's actually worse than just reading the string, but let's just focus on that. And so Dory, what do I want to say? Like what you can think of like KZG commitments and bulletproof commitments are closely related, where at least as far as the commitment itself goes. If you forget about the evaluation proofs, with KZG commitments are identical to bulletproof commitments, except in KZG commitments, the commitment key is what's called structured. And I can actually give a little flavor here for those who have seen trusted setups before. In KZG commitments, the commitment key takes a group element G, an elliptic curve group element, and there's something called toxic waste, which is like a random value tau. And the commitment key sticks a bunch of powers of tau in the exponent of the group element. So this is called the powers of tau, like trusted setup or structured reference string. And if you want to commit to degree n polynomials, you need n powers of tau in the exponent. Okay. And so the verifier for KZG commitments doesn't need to know the entire commitment key. It just needs to know G to the tau. Okay. The reason there's a trusted setup is because it's crucial for the commitment scheme to work, to be secure. It better be the case that no one in the world knows tau. That's why it's called toxic waste, right? So trusted setups involve like a whole bunch of people getting together, and they kind of jointly determine what this tau is, and they jointly generate this really big structured reference string, which has the first n powers of tau like kind of hidden in the exponent of this group element G, and because discrete logarithms are hard to compute, like nobody can kind of take these group elements and figure out what their exponents are, so no one knows what tau is. But if everybody who participated in the setup ceremony got together and sort of put their share of tau, didn't actually dispose of their toxic waste, and everyone put their shares of the toxic waste together, they could figure out what tau is and, break the security of the commitment scheme. So because the commitment key here, so if you did know tau, you know the whole commitment key, right? So the verifier only needs to know like G to the tau is how things work out. In bulletproofs, it doesn't want to have a trusted setup. So the commitment key is literally just n random group elements. And so whereas in bulletproofs, the verifier only needs to know G to the tau. In bulletproofs, in KZG, the verifier needs to know G to the tau. In bulletproofs, the verifier needs to know all n of these group elements. And so, the it leads to small proofs but a slow verifier. That's where the tension is coming from in bullet proofs, why the proofs can be slow, but small, but the verifier can be slow. Dory sort of does some cool stuff to get around that issue. So like the slow verifier in bullet proofs isn't fundamental, but Dory comes with these downsides I pointed out, like in terms of concretely the proofs get bigger and stuff. There's some other downsides that nobody is using it today. So I think that is kind of bullet proofs is sort of the main exception of like a small proofs but slow verification. I'd say the other place this sort of comes up is in pairings. So I think next session I'll discuss. I'll tell you like the main like operations that SNARK provers and verifiers do. That SNARK provers and verifiers do. And I think that's important to just have a brief overview of that as we start seeing how the SNARKs work, because otherwise I'll tell you how the SNARK works and you just won't have any sense of what the cost is. Because I think it's helpful, like as you see, in this SNARK, the prover has to do this, to just have a general, if vague sense of like what this actually costs to run on like a computer or something. And for, something like KZG commitments for the verifier, with KZG commitment based SNARKs, at least, like the main thing the verifier does is what are called pairings. So like the proof is, for when you use KZG commitments, might only be like a handful of group elements, I don't know, 3 to 10 group elements, depending on what SNARK we're talking about, 3 to 10 group elements. So very, very short proofs, okay? But the verifier might do like something like 3 pairings, 2 or 3 pairings or something. And each pairing operation is like as expensive as like thousands of group operations. Again, like you don't even have to know what a group operation is today. Like just, I'm saying stuff and expecting, many of you have no idea what I'm talking about. So my point is here, like the SNARKs based on KZG commitments, they do have like the cheapest verifiers out there. But the shortness of the proof might suggest that the verifier is even cheaper than it is, because the verifier has to do these pairings, and pairings are actually pretty expensive. Like a pairing takes as input 2 group elements and spits out a 3rd group element. And even though it only involves, 3 group elements, 2 inputs and 1 output, it's just, it's much slower than almost anything else you would ever do with group elements. So I think these are the main exceptions to keep in mind for why short proofs might not actually lead to really fast verifiers. I think in almost all of the cases, they tend to go together. Other questions?
Just one thing on this. So one thing that kind of stumbled me for a little while was this notation of g to the power tau, which essentially is g added tau times rather than multiplied, because I don't think.
Yeah. Okay. Good. So this is using multiplicative group notation. So here the group operation is treated as multiplication. And so this would be g times g times g tau times. Yeah. A lot of people like to use additive group notation now. That just means, so any group, yeah, if you don't know what a group is, don't worry about it. But any group comes with an operation, and you have to give it a name. And we normally think of it as, call it either addition or multiplication, but you're just choosing a name. Like either way, it's the same operation. A lot of people like additive notation, and for bulletproofs in particular, like additive notation makes a lot of sense for reasons we'll talk about, when we cover it. I like to use multiplicative group notation other than when covering bulletproofs, because I like to think of values as hidden in the exponent, right? So here it's like, we have all these powers of tau in the exponent of g. We have g to the tau squared, g to the tau to the n. And because, discrete logarithm is like a cryptographic assumption that refers to multiplicative group notation. It's, it says, hey, if I give you a group element like g to the tau for some tau you don't know, it's going to take you trillions and trillions and trillions of years to pull tau out of the exponent to figure out what tau is. That's called the discrete, so the discrete logarithm of g to the tau is tau, to base g. So I like thinking about things, values as, quote, hidden in the exponent of g. And that, that terminology, that way of thinking is sort of highlighted by the multiplicative group notation. That's where exponents come up. With additive notation, this would be denoted like tau times g. I think people would put the g in brackets, I think, typically. And then, I don't know, tau is like hidden outside the brackets. I just don't like it as much. I like thinking of tau is hidden in the exponent. But it's just a convention thing, whether you use treat the group operation as multiplication or addition. Was that a little bit helpful?
Yeah, I know this, but I think I struggled a bit, between blog posts. So just for everyone, it's just a notation thing. Same.
Yeah, no, it really trips people up, and so it's unfortunate. I think there's probably been a movement, is my guess, to sort of coalesce around additive notation, and I'm sort of a holdout. And the book uses both. It uses additive notation only when discussing bulletproofs and Dory, and otherwise it uses multiplicative. I just see the value in the multiplicative notation of, emphasizing that values are, in the exponent, like, no one knows what they are unless you are the entity that actually put the value in the exponent. You don't know what the exponent is. Okay. Other questions?
Where should we categorize FRI?
Great. All right. So I got one more category to go, and that's where Fry is. So the two categories I've covered are, trusted setup with elliptic curves, that the most popular variant being KZG. That applies only to univariate polynomials. Then there's the transparent, but still using elliptic curves, the most popular being bulletproofs. Bulletproofs, by the way, applies directly to both univariate and multilinear polynomials, as does Dory and Hyrax. Now, the third category is based only on hashing. There's no groups. And so these also involve error correcting code. So like you take, the polynomial you want to commit to, you take its coefficients, you apply some error correcting code to it. Don't worry if you don't know what that even means. And then you like Merkle hash the code word, and the commitment is the root of the Merkle tree or something. So this is hashing based. And here the most popular is Fry. And again, I'd say this is the most popular because in this category, it's the one with the shortest proofs. The proof size for the evaluation proof is about lambda times log squared of the number of coefficients of the polynomial. So that, n is like the size of the polynomial being committed. Lambda here is the security parameter. So think of this as about 128. And concretely, this means something like hundreds of kilobytes. That's how big the proofs are. And the proofs mainly consist of hash evaluations because they're hashing bits. And the other commitment schemes in this category are a commitment scheme from Ligero, a very closely related one called Breakdown. Ligero is basically a special case of breakdown. And then this led to something called Binius. And now there's sort of an amalgamation of like the Ligero breakdown Binius stuff. Is sort of, we figured out how to combine it with Fry to get something they're calling Fry Binius. Now, let's see what I want to say here. Certainly, Fry Binius is a multilinear commitment scheme. So I think like Ligero and Breakdown apply both to univariate and multilinear. But Fry Binius and let's say Fry Binius at least only applies to multilinear. Fry only applies to univariate. And again, you can turn it into a multilinear one, but that introduces overheads, which I think are significant. So there are a bunch of projects that are currently pursuing exactly that, transforming Fry into a multilinear commitment scheme, so they can use some check-based PIOPs, and I think they're going to run into significant overheads as a result. So I guess that maybe there's some disagreement about those overheads since people are pursuing that. But yeah, right. So Frey-Binius, concretely the proofs are a little bit bigger than Frey, but asymptotically they're basically the same. So you should think of these as also like hundreds of kilobytes to maybe a megabyte or so. Hundreds of kilobytes to a couple megabytes. But certainly concretely bigger than Frey by at least a factor of I don't know quite what it would be, like 2 to 5 or something. So concretely bigger than Frey. Okay, and again, this has been a controversial view of mine, but like so in this category, Frey has the shortest proofs. That I agree with. I guess and everyone agrees about that. What I guess is controversial is I think Frey has significant downsides for the prover, especially relative to the commitment schemes elsewhere in this category. So my view is just like all the other categories I put up here, both on the PIOP side and the commitment scheme side, there's a tension that seems to always be exhibited between prover time and verifier costs, and that the hashing based commitment scheme category is no different. So I won't go into the details today of the benefits for the prover of these other commitment schemes relative to Frey, but suffice it to say, I think there are significant benefits. So that is really the landscape. And again, you can pretty much mix and match your PIOP and your polynomial commitment scheme like at will, and like any combination will give you a certain cost profile, with the big caveat again being that there's some awkwardness if your PIOP wants to use univariate polynomials and your polynomial commitment wants to apply to multilinear ones, or vice versa. And there are some ways to bridge the gap, but my sense is like you really shouldn't be gap bridging that much. Like you really should combine some check-based PIOPs with multilinear commitments. And then if you want to get the proof size way down, you should take a constant round PIOP and combine it with a univariate commitment. And I don't really quite understand why some people want to kind of convert a univariate commitment into a multilinear one rather than just directly use a multilinear commitment scheme. But yeah, so that's the landscape. And I think the only other things to mention today are that one, you can get the best of all worlds, ideally, in terms of the costs, using SNARK composition. And what I mean by this is, you can take a PIOP with like a fast prover but bigger proofs, and combine it with a polynomial commitment scheme with a fast prover but bigger proofs. And initially, if you just stop there, you've paid a price for your fast prover because you now have bigger proofs and slower verifier. But you don't have to stop there. Instead, you can use a small proof SNARK to prove the big proof. And as long as the first SNARK's verifier is sufficiently cheaper than the original computation that the prover claimed to run, proving the first proof shouldn't be a bottleneck for the prover. So in this way, you can basically have almost no prover overhead, but get the benefit of the small proof and fast verifier of the second SNARK. Okay, so the story is not just take your favorite PIOP and take your favorite polynomial commitment scheme, put them together, and you're done. You can also then apply SNARK composition to mitigate any downsides of the resulting SNARK. And then the other thing to mention is what are called accumulation or folding schemes, which are not unrelated to SNARK composition. And so let me just tell you what these are, and then I think we'll wrap it up for today. And next session, again, I'll probably give an overview next session of the main bottleneck operations that SNARK provers and verifiers do, and how to think about their costs, And then we'll probably, that won't take the whole session, and we'll start covering, you know, like chapter 1 of the book and stuff. Okay, so yeah, I'll just say a few minutes about accumulation and folding schemes, and we'll wrap up for today. So first I'll give you, like, so these are things like nova and, you know, proto-galaxy and protostar, proto-galaxy and stuff like that. So there are different ways you can describe these things, but I would say, I like to describe them as follows. So one thing they're useful for is controlling prover space. Okay, so what's happening is if you don't use recursion, if you just look at, like, take your favorite polynomial IOP and take your favorite polynomial commitment scheme and put them together and get SNARK, and there's no SNARK composition or recursion done after that, okay, you have a very big problem with prover space based on today's current implementations, which is the prover space, like the prover space grows linearly with the size of the circuit it's proving it, like, knows a satisfying assignment for. Okay, and like, so the prover space can easily be many gigabytes, even for like really, really simple statements, even for really small circuits. So to put some numbers out here, I think like RISC-0 has gotten their prover space down to like 8 gigabytes or something. But like 8 gigabytes is only enough to prove like 1 million cycles of the RISC-V CPU, which, you know, is like, your laptop can runs like several billion cycles per second, right? So 1 million cycles is like 1,000th of a second on your laptop or something, you know, tiny. Like 1 million cycles is like nothing, and you need 8 gigabytes to prove it, right? So what people will do is they will chop like a big computation or a big circuit or something up into small pieces, prove each piece separately, and then like aggregate the proofs. Okay, and that way, this really space-hungry prover, is only applied to small pieces, like 1 million cycles of RISC-V CPU, and so the space stays bounded at like 8 gigabytes. Because if you try to apply the prover directly to, you know, 1 billion cycles instead of 1 million cycles, it would go from 8 gigabytes of space to 8 terabytes of space or something like that. And, you know, you just can't run the prover on, you know, reasonable hardware, or, you know, something like that. So this is also called like continuations. I think that's a term that RISC-0 coined. So breaking big computations up into small pieces, proving each piece separately, aggregating the results, that technique is sort of called continuations, and it's mainly done to control prover space. Okay, now where do accumulation and folding schemes come in? I guess another way of, I'm going to answer that question with another question, which is, like, why is the space usage of something like RISC-0 today 8 gigabytes and not smaller? Okay, and I believe the answer is, comes from how they have to aggregate the proofs. So the way a project that uses a hashing-based commitment scheme like Fry, you know, with most deployments today being examples, at least in the ZKVM space, they would aggregate the proofs as follows. You know, if I have a proof like pi1 for piece 1, you know, that I like ran the first 1 million cycles correctly, and I have a proof pi2 for piece 2 that I ran the second 1 million cycles correctly, and I wanted to aggregate the proofs into a single proof pi, what I would do is pi would like prove that I know pi1 and pi2. All right, and I'm waving my hands a little bit, but that's roughly what's going on. So this is what I call proof aggregation via brute force recursion, SNARK recursion. You know, so I aggregate like 2 proofs by proving I know both the proofs. Right, and what this requires you to do is take the SNARK verifier for pi1 and the SNARK verifier for pi2, turn them into a circuit, and then prove I know a satisfying assignment for that circuit. Okay, so now to get back to the answer to my question, like why does, you know, like existing ZKVM projects use like at least 8 gigabytes of space today? The answer is because like turning pi1 into a verifier circuit and pi2's verifier into a circuit, and storing those circuits, that takes 8 gigabytes of space, right? Like, so what's going on is like the recursive verification itself, like can't really be broken down. Like that's sort of where like the smallest piece you can break anything into. Like you can't really break C1 into smaller circuits or C2 into smaller circuits or something like that. And so, so the size of the SNARK verifier turned into a circuit is like what's bottlenecking prover space today. Okay, so coming back to accumulation and folding schemes, they avoid what I'll say. They avoid brute force recursion. So what I won't go into detail. I'll just say they avoid ever taking an entire SNARK verifier and turning it into a circuit the way brute force recursion does. And as a result, they are able to break things up, break big computations up into much smaller pieces. So something like Nova or Proto-Galaxy or something, they can break big computations up into smaller pieces compared to anything that uses Fry or something like that. Than what you can do with brute force SNARK recursion. And as a result, they can get much smaller space provers. There are still some challenges with these accumulation and folding schemes. You actually can design SNARKs directly from them. So they kind of circumvent the polynomial IOP plus polynomial commitment paradigm a little bit by leaning very, very heavily on some kind of recursion without it being like brute force SNARK recursion. I know I'm saying words that don't make much sense if you haven't actually seen these protocols before. And so I mean, people are pretty excited about them. I think with good reason. I think they do have a reputation for potentially being pretty fast. I actually think their main benefits come for prover space. Like I said, they can break things up into smaller pieces than can techniques that use brute force recursion. Really, this is essentially only known how to do this stuff with curve-based commitments. There's been some work trying to extend accumulation schemes to hashing-based commitments, but they have significant overheads still. And so, I think it's fair to say, at least today, if you want to go the accumulation or folding route, you're going to have to be happy with a curve-based commitment scheme. Another thing I want to mention, which seems to not be widely known, is there are ways to control SNARK prover space without recursion. And I actually think that that is a very promising approach that potentially might sort of replace accumulation and folding schemes for that purpose in the long run. And so I can say more about that in some other session. But yeah, so I'd leave it there. You should at least know that these accumulation and folding schemes exist, and that one of their main benefits today is for keeping the prover space under control, and in particular, they can get the prover space lower than what you get with brute force SNARK recursion, and that's why you see a project like Aztec is using folding schemes today. It's using something based on like Proto-Galaxy as an example, and that's because they're like a privacy-focused application, and this means that the prover is going to run in a browser. And if you want the prover to run in a browser, especially if it's on a phone or something, you really need that prover to have like 1 gigabyte of space or less, something like that. And the folding schemes today are like the only way we can get the prover down below 1 gigabyte of space unless you have like some really, really, really simple statement being proven anyway. So I'd say that's the landscape. And next session, I can go into a little bit more detail about like why there are these trade-offs, this tension between prover costs and verifier costs, and like why I consider certain popular SNARKs that are very efficient for the verifier to be slow for the prover, like where that's coming from, what that view is based on. I think it's helpful to have some discussion of what the provers actually do and what those operations actually cost, and what certain kind of accepted wisdom about SNARK design kind of posits about prover costs and whether that accepted wisdom is precise or not. So I'll plan to start next week with a discussion of that flavor, and if assuming that doesn't take up a whole hour or something, we'll start chapter 1 of the book. Okay, so thanks for coming. Hopefully the technical issues at the start weren't too bad. I can stick around for a bit if anyone wants to ask some questions, but this is the content I had for today. So thanks again, and I hope I'll see you next week.